Hi everyone, I'm Tony Sanjanola. I'm a blockchain engineer at PayPal. I actually started my journey as a blockchain engineer way back in 2017. I remember the first time I heard about Bitcoin. I'll be honest with you, I actually thought it was a scam. But 2 years later, I ended up doing some more research, watched the video about Italian Buterin, and I was sold on the idea of building decentralized applications. I started going for hackathons, won some, lost some. I eventually started auditing smart contracts during the ICO bubble. Those were interesting times. I actually went as far as going to EdCon, the Ethereum Developer Conference, which was held in Toronto, Canada, back in May 2018. And when I did that, I actually pitched a blockchain healthcare idea on stage to the Ethereum founders. Vitalik was there, Vlad was there, many people, many notable people in the Ethereum ecosystem. I did receive funding for that startup. It was a blockchain healthcare startup. Unfortunately, that failed. But moving on, went full time into blockchain development. Since then, I've built different kinds of blockchain applications, developer tools, deployment tools, infrastructure, blockchain frameworks and protocols. I was actually up until joining PayPal as a blockchain engineer. I was actually working as a core contributor to Hyperledger Aries. So Hyperledger Aries is just a digital identity. I think it was a digital identity kit, toolkit or framework. So I actually built out the mobile components in there so that you can actually, in the future, blockchain enabled applications or mobile apps that use digital identity or self-sovereign identity will have an agent within them. So I'm actually the one who built that. Fun fact. Yeah, so I've worked on different kinds of use cases. It's NFT, ERC20 tokens, healthcare, insurance, finance, real estate, stuff for the government, or government agencies, I should say. And I've really been all around the space, and I've had the opportunity to actually see what blockchain technology is in reality. I can tell you there's a difference between what's taught in theory and what you actually do when it's time to code. So I'm going to do something like that today. We're basically going to do that today. And yeah, please remember to like this video, subscribe, comment down below if you have any questions as you watch this. And don't forget to share this across other platforms. All right, let's dive right in. Okay, before we start, I do want to let you know we have a Twitter page. So just head over to twitter.com/web3coders and hit the follow button. For you, there will be a follow button here, and stay in touch for all our updates. Then visit our website at web3coders.com. When you go there, what we currently have is a simple registration form. All you have to do is put your email in there and subscribe so that you're announced for our upcoming blockchain developer programs, education programs. And don't forget to visit our Discord. We have a Discord group. So just hit the link and you would receive an invitation to our Discord group. Okay, now getting in to what we have to do today. Okay, so what exactly are we trying to solve? It's no surprise that there's been a lot of discussions about COVID-19 vaccines and certifications, being able to prove that you've indeed received your vaccination, either at the border or during while you're traveling, or even just when you're visiting an area in town that will be congested. So before we start, what we want to do is to look at three scenarios within the last month, within the last few months, I should say. So over here, we have a case where many people's vaccine passports were actually rejected due to fraudulent claims. Right, so there are people who presented their vaccine passports, and what they actually presented was fraudulent. Then what ended up happening was they were denied entry into the border. The second use case, second scenario is the WHO suspending the approval process for a specific vaccine, COVID-19 vaccine. And this is due to inspection issues at the manufacturing plants. Then we have a situation where many people presented valid and original COVID-19 vaccines, vaccine certificates, but they were denied entry basically because, or suspectedly because the country at the port of entry didn't feel that the origin country had provided a good data source that would be used to verify that the travelers from that country, from country A, were actually indeed vaccinated. So by the time they got to country B didn't have any database from country A to access and say, okay, all right, you're vaccinated, you're not vaccinated. So those are three things. Now, what we really have to do is think of how we want to solve these problems. Well, actually, not so fast. We're not going to jump straight into code. As you know, before you write anything, you need to actually plan what it is that you're trying to accomplish. And you also need to come up with a good set of requirements, the use cases, the system design, and so on. So that's what we're going to do first and foremost before we go into development. Okay, so I've already gone ahead to create some of these. Okay, so I've already gone ahead to create some of the documentation because I'm sure you don't want to watch me write documents. Okay, cool. So what are we trying to set out to do? Right, we want to design and implement a system that solves a known problem of trust in the COVID-19 vaccine supply chain. Right, so we'll get to trust in a second. That's actually very important for anything you're trying to do with blockchain. Now, in terms of requirements, we had an overview of what some of the what the supply chain looks like for in general, and also for COVID-19 vaccines. Over here, we can see something that is much more accurate and more specific. So you have a manufacturer who passes on the vaccines to an international logistics company. That company passes it on to the national storage facility. This is the cold storage that keeps vaccines at a temperature that would maintain their quality for about 30 days or so. Then you have a national logistics company move some of those vaccines in batches to regional hospitals. You then have the regional logistics company or the hospital themselves sending out the vaccines to a health center, such as a smaller hospital or a clinic, or even possibly a pharmacy. And this could go on and on, depending on how small the environments, how small, how far the landscape is. Okay, so who are the system actors? Based on what we saw above, obviously there's the manufacturer, there's the distributor, there's an inspector, there's going to be the storage facility. So you see the inspector wasn't described here, but you would be sure that definitely someone has to perform quality checks on the vaccines at key points of the supply chain or the cold chain. You have the immunizer, who also isn't, who's represented here. The immunizer could be a doctor or a nurse. They vaccinate people and provide vaccine passports and certificates. Then you have the traveler, who isn't shown here, but they're the, think of them as the patients, or just you and I. And they're the person who received the vaccine. They get their certificates for the vaccine. Then they actually present that, if they are traveling, they present that vaccine certificates or passports at a border of the destination country. Finally, you have the border agents, who also isn't displayed in the diagram above. They're the ones who will ensure that everyone who's coming in actually has a valid vaccine passport. So based on the news articles we saw earlier, what exactly are the problems? How do we map the problems to some possible solutions? So the first problem we identify is that vaccine passports can be falsified, right? And who does that affect? That affects the border agent and everyone in the destination country potentially. So the border agents really has to ensure that they have a way to verify the certificates. So what we can provide for them is a feature to cryptographically verify the certificates using on-chain data. Then the next problem is that the key facilities may not meet quality standards. So key facilities here refer to the manufacturing plants or the national storage facility, where things have to be kept in cold storage. They may not meet quality standards. Who does that affect? That affects everyone. What would need to be done is that when the inspector provides certificates, they will need to publish that to the blockchain for it to be immutable and transparent. Then there also needs to be a way for others in the chain to easily verify the presented inspection results. Thirdly, we have the third problem is that vaccine passports may not be recognized by destination countries. So who does this affect? The international distributors. So that's here, right? Imagine you have an airline and you have a cargo of vaccines, and by the time you get there, right, you're told that after inspection that the destination country doesn't approve of the vaccine, right? That's a waste of money. For the traveler, imagine that once you get to a country, you then find out that, they don't accept this vaccine. Now you have to go home, right? What would you then do? You would then tell your friends, families, and everyone on Google reviews that the immunizers wasted your money, right? So that's also bad for the immunizers. So this is almost everyone, but not just quite everyone. So what could we do? We could provide a feature that allows them to verify the signatures in presented certificates. Okay, so why blockchain? Right? Why do you need blockchain for this? Why can't you just use something else? Well, we need tamper-proof provenance, right? We need to be able to clearly answer the question, which states, does the label on the vaccine's vial, right, accurately represent the contents of the vial? And did the vaccine come from an inspected batch, right? That's the provenance. Can we see the trace, right, in the supply chain of this vaccine? Then next is credential issuance and verification, right? So using blockchain technology and the libraries, as we'll see soon, you can cryptographically sign messages, right? And then easily verify those with on-chain data. So the issuers of certificates, such as the immunizer, or the doctor who gives the vaccine certificates, or the inspector who certifies that a facility is good, right, they can issue certificates and everybody else can verify those certificates. Then of course there's data redundancy, right? Data can we don't want data to get lost when the traveler is moving around, right? So we want this to be accessible on the blockchain. So all they need at the end of the day is really just some ID or QR code. So the data, we also don't want the data to be lost in transit. So even if the vials were to get damaged, at least we still want to have that record. Now, okay, all right. At some point, these vials, before getting damaged, this was the state of their certificates. So from a system design perspective, right, what's sort of like a high level flow? So there's going to be the inspector issuing the certificates to the manufacturer, right? Then we update the status of the certificates to manufactured, right? The manufacturer presents that certificate to the distributor, right? So that's the international distributor. Distributor verifies the certificates, right? Status updates to delivering international, right? On arrival to this location, the national storage facility, right? The distributor will then present it to the storage facility who verifies it again. Then they would store it, so the status is changed to stored. Then the storage facility would have to present that to the local or regional distributor, right? That then gets passed on so all the way down till it gets to the immunizer, and then the patient or the traveler is finally vaccinated, and that traveler presents it at the border to the border agents, who can easily verify the passports, the vaccine passports, based on the infrastructure that we'll be building. So if you notice, there's sort of like a common flow, right? There's this issuance, and there's presenting certificates, and then there's the verification of the certificates. So this isn't actually a new idea. Let me just increase the screen size a bit. Okay, that didn't go. Okay, maybe not that large. Okay, so the immunizer and the inspector, they always issue certificates. So we can classify them as issuers. The manufacturer, traveler, and storage facility, they always have to prove something. So they always have to present and prove that they have a certificate. So they're approvers. Then you notice the storage facility once again, the different kinds of distributors and the border agents, they are verifiers, right? At some point in time, they always need to be able to verify that what they're being given is indeed valid, right? This saves them the hassle of losing money, right? The distributor doesn't want to spend money going all the way somewhere. The border agent doesn't want to take the chance of letting someone into the country without a valid vaccine certificate. Now, so if we look at the use cases, right, we can boil down the flow up here to these three primary use cases. As an issuer, I can issue a signature representing a digital certificate for a manufacturer's plant or storage facility, right? This could also apply to the immunizer, issuing a certificate of vaccination to the traveler. Then as a prover, I can present a certificate of signature that has been issued to me. Then finally, you have the verifier, who can validate the signature on the blockchain that's stored on the blockchain for a specific vaccine certificates. So what are we not covering? We're not going to touch on payments between system agents. For example, if you're traveling, you know that you have to get a, I think it's called the PCR COVID test, rapid COVID test, something like that. So you have to pay for that, but we're not covering that. We're not looking at edge cases where some doctors are dishonest, right? The traveler just needs to go to the immunizer's office, right, or facility, and get immunized. If you were to go to the doctor, you wouldn't take your phone and start scanning the QR code on everything they give you there, right? If you don't even trust the doctor, then the whole thing is that's pointless. We're not looking at how suppliers will send raw materials to the manufacturers. We're starting our supply chain from the manufacturers. We're not looking at image capture or QR code scanning. We'll just simplify it.
We're not considering scalability of this system. We're not building this to be, something for 10 million users or whatever. This is specifically just a proof of concept. And distribution to areas without internet access, IoT, machine learning, regulatory compliance, GDPR, but of course, as we're coding, we will try to make sure that we're not doing things where we log personally identifiable information to the ledger, to the blockchain. And pretty much anything that isn't addressed in this video and these videos won't be, anything that's not addressed in this tutorial won't be in scope. Okay, so let's look at a high-level diagram. This shouldn't look too unfamiliar to most people. Over here on the left, right, you have your clients, so the issuer of a certificate, the prover, and then a verifier of the certificates. The clients make requests to a server, right, whether it's implemented in Node or anything, something else, Python, Java, and then finally to some data store. So this is your common three-tiered architecture. So in blockchain, you generally have this kind of approach, right? Some people, so because many blockchains can run smart contracts, what that means is that they can store, they can play the role of both the application or business logic layer as well as the data layer. So the three-tiered architecture, right, also applies to blockchain. Some people would also go as far as creating a separate database here, or even having caches all around. Okay, so that's one architecture style. The second, which we'll actually be using in this tutorial, is the dapp architecture, which is really just two-tiered, right? The clients directly hit the blockchain. They don't go to any server or anything, which means that these clients must actually have logic within them to be able to make the right connections, as well as parse data back and forth between the blockchain. So we will deploy smart contracts to a blockchain and interact with those smart contracts directly from the clients. Okay, so that's pretty much it with regards to this requirements documents, or think of it as our plan. So let's go over to Remix. So we're going to search for Remix IDE, that's the Ethereum IDE, and let's start coding. Okay, so the first thing we're going to do is just have a quick look at the layout if you haven't seen this before. On the left, you have your control, I guess we could call it the control pane. Here is where you see, this is your file explorer. So basically, this is a web-based IDE that has Ethereum, a lightweight Ethereum virtual machine running inside of it. So over here, you have your compiler tools. Here you have your deployer tools to deploy to that virtual machine in the browser. You can see you have different environments to work with. We'll be using the virtual machine that says London. That's the latest version of Ethereum. Then over here, you have just extra plugins. Okay, so in your file explorer, you would see that we have a few different things here. You have your contracts file. So your contracts file already contains some existing code, but we're not really going to touch any of that. All you need to do for now is just create a new file. So you click this button, and then let's call it cold chain.sol. Okay, I may have to zoom in here because it is. Okay, yeah, it is a bit small. Okay, can I close this? Yes, okay. All right, so coldchain.sol. What we're first going to do is define the version. So what this does is that it tells the Solidity compiler, by the way, we are writing in Solidity, that's the programming language we'll be using. So this tells the compiler, Solidity is a compiled language, and it's static. a statically typed language. So what we're going to do is define what version of the compiler we want to use. So we're saying anything greater than or equals to 0.7, but less than 0.9. Solidity tends to release versions like almost every day. So first thing we're going to do is define a library. So based on our use case, we know that we're going to be doing some things with cryptography. So what we're first going to do here is create a library called CryptoSuite. What we're going to do is look for existing code on how to, okay, and what we're going to do is define two functions. The first is a function called split signature, right? It takes in a variable called bytes, called sig of type bytes, okay? And you see I'm using the keyword memory. So bytes, this is one keyword, one data type rather, using Solidity. There are other data types as we see. Memory just says that we want this to be temporary. This is just a way to save space at the call. So we're going to say internal, meaning that we just want to keep this within the scope, and then we're calling this pure. So we're saying that this function is a pure function, meaning that it doesn't change the state of anything. You just produce, you provide it with an output, and it just produces the results. Then we're going to say uint 8 v bytes 32 r bytes 32s. Okay, so these are the return values that we're going to be sending. Again, you see that there's a new data type, uint 8. So this is unsigned integer of size 8. You have bytes 32, right? So that's the different. These are just examples of other data types. So here we're going to say require signature.length to be exactly 65, and that's the condition for a valid signature that would require others to sign. So we're going to say return VRS. So how exactly do we do that? You see I've created this assembly, I've written out assembly here. So basically when you see this in Solidity, what you're doing is you're accessing the virtual machine, right? That's your Solidity code or program will be running on, and you're actually sending instructions to that virtual machine to make some low-level changes. That probably sounds like a very bad thing to do and sounds chaotic. However, that's this is the approach used in Ethereum, right? You generally don't, make changes to the train, the chassis of the car. You don't just open up the bottom of the car and start making changes when you're driving. So this is new. This is something that will be new for people who are working from other languages. So I'm going to say add signature. So you can see I'm using some words that sound like opcodes if you're familiar with operating systems, right? The way, so what this does is we get the first 32 bytes, right? The way that Solidity works, or Ethereum in general, is that there's a virtual machine, right? It's called the EVM, the Ethereum virtual machine, right? It's a stack-based virtual machine that's running on the blockchain, right? That's the difference between Ethereum and okay, sorry. Yeah, next 32 bytes. So the first 32 and the next, so this will be 64. So that's the difference in Ethereum and Bitcoin, right? Or Bitcoin kind of networks. Ethereum actually has a virtual machine, last 32 bytes, a virtual machine installed on it. So each node, right, each client software is actually running a virtual machine within it. So here we're just going to say bytes 0 and then mload. Okay, this is 96. Okay, Now we've written out the library for the first function in the library. The next function that we need to use is going to be called recover signer. Okay, so what this does is that this function would actually call the split signature. Okay, so we would receive some message, right? And we would also receive a signature, right, for the message. Right? And essentially what we want to do at the end of the day is figure out, is to extract the signer of that message, right? So to do that, we'll be using something called recover, right? But in order to first use that, we have to first get the values v, r, s, right? So we need to extract that from, I'm sure you guessed it, the split signature, right? So that's where that's where that function comes in. Okay, so we're going to extract v, r, and s, and then we're going to return recover. So that's a default method that you can call anywhere in your Solidity file. So we're going to pass in the message, then the broken down signature, right? The split signature. This will then return, as you can see, a new type address, right? So this is the actual address that signed the transaction, signed the message. Okay, so we're going to just close this library, right? And now we can move on to our actual contract that you want to see. So that will be called cold chain. So we're going to say contract cold chain. Okay, so we're going to create a status. Let's call this certificate status. Right, so we're creating enums. So if you're familiar with other languages, this shouldn't be too confusing, right? Enums basically are a way to just represent some kind of constant. So here we're going to say delivering international, stored, delivering local, and then finally delivered. Right, so this is just what we had in here, right? These statuses. Okay, so delivered. Okay, now we need to actually represent the object itself of a certificate. So you notice I didn't say class, I said contract. So in Solidity, you don't actually have classes. You have contracts, right? You have libraries, you have interfaces, and within you can actually define structs, right? And the contract. So for anyone who's written something like Golang, you can see that this kind of looks familiar. So we're going to give this an ID, and then we're going to need some issuer, right? The certificate needs someone to issue it. So let's call that an entity, which is another struct that we'll define. Now create another one called prover. So someone has to hold, someone has to be the subject of that certificate. Then finally, we're going to say, well, not finally, because we still need to add the status. We need to add in the signature, right? So the signature for that certificate, and then we're going to add the status. Okay, so it's this signature that would eventually be passed in to this in here, right? When we want to verify the status of the signature within the certificates. Okay, so let's create a new enum called role, or we can say mode. So there were different kinds of agents or entities that we saw, right? Verifier. There were the issuer, prover, and verifier. So what we're going to do is create a new struct called entity. And then we're going to give it an address as the ID, right? So that's, we could always just call this entity, or you could just call this private public key. ID should be fine. I can just give this a role. and then uint certificate IDs. So we want to keep track of all these certificates that this, okay, that we're going to say mode, right? So what type of entity are they, right? So let's actually call this entity type. Okay, so what type of mode are they operating in, right? Because as you saw from the diagram, sometimes someone could operate as a prover and other times as a verifier. Then we're going to add uint array of certificate IDs. Okay, so we want to keep track of all the certificates that this entity has been involved in. So let me actually move this a bit higher. Okay, now the next thing we want to do is to actually define our vaccine batch. So we're not going to have, you know, individual vaccines. We're just going to keep track of batches. Okay, so we're going to say uint ID string brand, right? So what's the brand of the vaccine? Then we're going to have a manufacturer. So the manufacturer would also be someone on the network, right? And they would have their own identity. They're going to have, of course, for this batch, right, all the certificates that have been issued to it, right? So that batch. Okay. Then we're going to create a constant, it's public, using the constant keyword. I will call this max certifications. And the reason we do that is we want to be sure that certificate has not been verified more times than it needs to be as part of the verification process. Okay, so we create the certificate IDs, right, to keep track of all IDs of the certificates. And you'll see why in a second. With Solidity, there is a bit of an issue with really just, creating objects and looking them up, or I should say structs, and looking them up in general, right? So what we want to do is to create some kind of key value pair. To do that in Solidity, you say mapping, and then you have your key type mapped to your value type. So we can make this public and then say the vaccine batches. Okay, so in Solidity, if you use the keyword public on an instance variable, right, that actually allows tells the compiler to create an automatic getter function. So you don't always have to write extra getter functions unless you want to do something specific with what you're trying to get, right? Solidity would automatically create a getter function for you. So here, the certificates, and I should just copy that to make things easier. Here, we're going to have an address. As you notice up there, the address is what we use to identify the entity, not a uint. So this would be entity. This would be entities. Okay, and then we're going to create something called an event. So what events do is after they allow you to communicate to anyone who's listening, to any listener, that an operation has occurred on the network. So you can do that from your smart contract. You can emit an event into the blockchain. So we're going to create one called identity so that we know when the entity has been added. All right, I'm going to say this is string mode, entity mode, sorry, type string. I'm just going to copy that a few times. Okay, so I'm going to add vaccine batch. So we know when the vaccine batch has been created or added to the blockchain, right? Because if it's not added, then there isn't going to be a way to be able to verify it's on chain, right? So for this, we're going to say indexed, right? And use manufacturer. So why are we indexing the manufacturer? Right? If you have index, then think of it as an index in your database. You can do a faster lookup. So this way we can see whoever is listening can just listen for events, or focus on those who filter by this manufacturer essentially. So we can also issue certificates, right? And we can index that, right? And then we'll say issuer, so that we can see everything that's been issued by them. And we can add another address for the prover of the certificates, the person who has to present that certificates. So we can also just find all the certificates that they've ever been issued. And then finally, we have the certificates ID. Okay, so for the actual coding, well, I mean, we've been coding, but for the actual logic, oops. Okay, what we want to do is create a function called add entity, right? So it takes in an address representing the ID of that entity, and then it takes in some mode that the entity is operating in. So I'm going to say public and expand this. Now we will need some way to convert the mode into, because the mode here is a string, right? So we need a way to convert it into an enum in Solidity. So we need to do some kind of unmarshal. If you're coming from a background like Golang, you don't know the unmarshal keyword. Some other languages might say deserialize. I think in JavaScript, is it JSON.parse? Yeah, something like that. So let's go implement that function. So let's say function on Marshall. So it takes in some string mode. And we say memory. Okay, and we can just make this private, right? We only want this to be used within what we're doing, within our contract. Like nobody else needs to access this. So we're going to say bytes 32 encoded, or we could just say the raw mode, right? Actually, yes, encoded. The encoded mode is going to be, what we have to do is we have to do a type comparison. We have to do a type check. Right? So we need to compare. In order to properly compare in Solidity, you use an inbuilt hashing function. So kekek 256, right? And what you pass in is your ABI, another, so this is globally available in Solidity, using this function, encode packed. Okay, and this is what we pass in, the raw string. Okay, so what we get back is the encoded as bytes 32. So from string to bytes 32. So we're going to just copy this and paste it a few times. And here we're going to say encoded. Let's call this mode 0, mode 1. Since they're enums, usually the enum value results to integers. So say issuer, prover, and then verifier. So now what we want to do is to perform a comparison. So we're going to say if encoded row equals encoded So we're going to say if encoded mode equals encoded mode 0, right? And we return, return mode dot issuer. Else if, actually, let me just copy this. Okay, else if it's mode 1, then we'll say this is the prover. If it's mode 2, we'll say this is the verifier. Now, if it's none of these, what we'll do, if it's none of these, what we'll do is we'll call the revert function, right? What that does is that it just reverts the transaction. So we'll see, and this is again an inbuilt function into Solidity, invalid entity mode. Okay, cool. So now we can go back to writing our add entity function. So what we're going to do is say uint array memory certificate IDs. So we just want to create some want to create this array. Say max certifications, right? So add that size. I'll say entity memory. Now we want to initialize the struct. Entity equals, I should have chosen an easier name. Entity of ID mode, right? So now we have the actual mode and the certificates IDs, right? Because that's what we defined. So we're going to add this into the entities array. Let me just say entity. Okay, and emits this event. So entity the ID and the mode, right, has a string. Okay, so that's that. Then we need another function called add vaccine batch. So what we're going to do, let me just see if I clone these two and then just manually change things. So add vaccine batch, right? So that's going to take in a brand, right? If you remember, so the vaccine batch contains brand and manufacturer and a few other things, but what would receive from the outside would be these, only these two. I need the address of the manufacturer's an address. And let's say this returns the vaccine ID, the vaccine batch ID. Okay, so what we're going to do here is instead of all this, we're doing all this. So we're just going to say uint. Okay, we did need this one at least. Okay, so we're going to call this the certificates IDs, yes. And then here, we're going to get the current length of the vaccine batches, batch IDs dot length. So just the IDs, right? That tells us how many they are. So obviously this is currently 0. So this is going to be vaccine batch. And there's going to be, we're passing the ID, passing the brand, and the manufacturer. So now we can say vaccine batches. Let me just put this down. Batch, and this is actually just ID. Okay, and then we have our vaccine batch IDs, the push ID. Okay, so this was talking about with like the weird thing in Solidity, where you need to create all these extra methods and functions in order to be able to properly look things up. Now we're going to finally return that ID. Right, so that's what's being returned here. I just noticed I have a spelling error. This should be mode. Okay. Okay, cool. So we don't actually need this. So this is actually for the next next function. So we have we have our vaccine batch function. Yeah. Okay, so we actually don't need this one. Okay, so next thing is to issue a certificate. Right, we need to issue a certificate. So the next thing is to issue the certificates. So I'm going to create a function here called issue. That's going to take an address, issuer, address, prover. Oops. So you might notice I'm using underscores, which may not be the best practice in many other languages, but it has become sort of a convention in Solidity. Also, for readability, I will be moving these lower. Okay, status. Then you have the uint for the vaccine batch ID. And have your signature that we spoke about earlier. Okay, so what kind of function is this? This function is public and returns a uint, right? So which would represent the certificate's ID. Okay. All right. So first things first, we need to get the rights. We need to check that the issuer, right, is indeed, first of all, exists, right, and is indeed an issuer, right? So let's say we'll pass this in, and then we'll say require issuer.role to equal role.issuer. Okay, and next we're just going to copy this. Now let's call this the prover. So prover.role must be, oops, no, prover. Okay, now after this, we need to get the status. Okay, yes, this is where we needed the other function. We need to extract the status the same way we extracted the mode. Okay, I keep writing role. That's what I have in mind. Entity type, entity role. Next, we'll say Marshall status. So we need to create a new function. And we'll pass in the status string. So let's go above, copy, paste. All right, so we're just going to do something very similar. So instead of mode, status, Yeah, you don't have to name the return types. That's fine, but it's sort of nice to have the names there. Okay, so encoded. Wish I could do a find and replace. If only the ID did that. Okay. Okay. And now in here, we'll receive our status. So we had, I think, about 5 statuses. How many did we have? It's 1, 2, 3, 4, 5. Yes. So the first one was manufactured. Next was delivering international. Next was stored. Okay. Next was delivering local. The final one is delivered. Okay, let's just make sure we update these indices. And here we're going to say encoded status. Status dots. Yep, so just copying and pasting. Okay. Let me just delete these and just make them again. So I don't have to type too many times. Okay, so status 1. If it's status 1, then it's this. If it's status 2, then it's this. If it's status 3, then it's this. If it's status 4, then it's this. Okay. Yep, so we received an invalid, oops, certificate status. Yes, that's what I called it. Okay, to make things easier, I'm just going to change the name to status. Okay, all right, so now we have this marshal status function, which we will use in here, right? So that gives us back our status. Okay, so once we have it back, what do we then need to do? Right now, we actually have to figure out how to get the certificate, right? Also, how to create a certificate. So let's give it a new ID, right? So the ID will just be the current length. And here we're going to say certificates, memory, certificates equals certificates. Passing the ID, the issuer address, no, issuer entity, yes, not address, prover entity, signature, and status. Okay, next we're going to update the status. So right now we're issuing the certificate. So each time we issue a certificate, we update the status. So we're going to say, let's just have an initial certificate position. Okay. To represent the number of statuses, because we can only have 2 max certificates. So we're going to say if status equals status dot manufactured. If it's status dot manufactured, okay, if it's, yeah. Okay, so next thing we're going to do is to just create a vaccine batch, storage batch equals vaccine batches of vaccine batch ID. And then we're going to say batch.certificate IDs of this. Okay, so now what we're going to do is push that certificate into our certificates, our global list of certificates. So here we're going to say certificate IDs dot length, right? So we just update that length to indicate that we have a new one. And then we'll say certificates of certificates IDs dot length -1. So the last one is going to be this certificate. Okay, now finally, we just need to emit the issue certificates function. Events, sorry, not function. And we're returning the certificate ID, so the position. Say certificate IDs dot length -1. Finally, we're going to have the function to perform certificate matching or signature matching. So we're going to say is matching signature that receives the message uint ID and the address of the issuer. This should be public because we want people to access it. It's view because all it's doing is just checking the state, right? It's not changing the state of the contract. Okay, and in here, what we want to do is create the certificates. So certificates memory, or fetch it rather. Let's just call the cert equals certificates at ID. Okay, and now what we first want to do is require that the cert.issuer.id equals this issuer. All right, that's been passed in. Okay, if that doesn't work, require we just send it back. So it's be a failed transaction. So we'll say address recovered signer. Now we're going to use our crypto suite function. Right, so we have the recover signer function, right? And this is where we pass in the message and the certificates dot signature. Right, so the stored signature, right? That signature that was passed in here, right? This one that was stored. Now we're trying to verify it. So now we will return the recovered a check that the recovered signer is equal to the ID in here, the address. So recovered signer is an address, if you remember, like I mentioned before, right? This would send back an address. Okay, so that's pretty much it. So once again, in our library, we have two functions. One to split the signature, another to recover the signer, which calls the split signature and then calls the EC recover, right? EC recover. So we can close this. Then we have our cold chain contract, which creates the necessary status structs and enums, and then just creates the functions that we need. So here we're going to try to compile this contract and see what we get. Okay, so we have one error, and that is, yes, missing. Solidity. Entity Oh, 7. Oh, I kept thinking of roll. So let's compile that again. So certificate IDs dot push. Let me see. Did I mean certificate? Yes, that's what I meant. Thank you. IDs. Okay, so just some bug fixes and things to clean up there. Okay, so thank you for getting to the end of this video. If you want to see the next video in this tutorial, please make sure to like this video, add comments and feedback down below. Also subscribe to this channel and press the bell icon, as well as share this around with others. Look forward to seeing you next time. Bye.